Okay guys, so in this video my intention is to run through a practice of test 3. So you can see here test 3 is 16 problems. So I'm all ready to go. I've got any notes I want handy. I've got a calculator, scratch paper, and I've got my web browser has been set up so that I have everything I need bookmarked. So yeah, what do we got going on here? So it says the names and chemical formula of some chemical compounds are written in the first two columns of the table below. So what you get from a chemical formula and a chemical name is you can tell whether it's an ionic compound, or a molecular compound, and then you can tell whether the compound is an acid or not if it is a molecular compound. So what we've got to do here, it says each compound is soluble in water, so it will form an aqueous solution. And it says imagine that a few tenths of a mole of each compound is dissolved in a litre of water. So water is going to be like the major component. Water has a molar mass of 18 grams per mole. So in a litre you have 1,000 grams, you have many moles of water. So water is the major component. And then it says, then write down in the third column of the table the chemical formula of the major chemical species that will be present. Well, in every case, water is going to be present because that is there in a very large amount, and water is present as water molecules. So we're just going to write H2O. So what this is really about is understanding that ionic compounds that are soluble in water, they dissociate. All right. So ionic bonds can be pulled apart by water molecules, but covalent compounds don't dissociate unless the compound is an acid. Now, covalent compounds can't be disrupted by water molecules. So what that means is that the atoms that are held together via covalent bonds within a polyatomic ion don't dissociate. So atoms within polyatomic ions don't separate. And we might see that in this problem. So let's have a look. The first thing I'm going to do is go through and identify, do we have any ionic compounds and do we have any covalent compounds? So this guy is ionic because it begins with a metal. This guy is ionic because it begins with a metal, and this guy is covalent, and I know it's not an acid because its formula doesn't begin with hydrogen, and also because its name doesn't involve the term acid. So in every case, we're going to put the species water. Now what happens to our ionic compounds? They separate into the components, cations and anions. So potassium is in group 1A, so it is +1, and then the cyanide anion, I know it has to be -1 because these two are combined in a 1-to-1 ratio. So I can look up the charge and formula for the cyanide anion if I want, but there's no need to. So for the first one, those are the three major species. I'm asked to put them in separated by commas. So that's it, all right? So there we go. All right. So yeah, I think we've got that one worked out. Now what about the next one? Well, again, water is going to be present as the greatest component, and then we've got, it tells us that these are copper 2+ ions, copper 2+ ions, and then the chloride anion, we know that chlorine is in group 7A, so it must be -1. So that's the answer for the second row. Now, the third row there, glycerol. Glycerol is a covalent compound. So what that means is that these molecules, they don't dissociate. They remain as intact molecules. So again, water is going to be present because it is the major component. We have many moles of water. And then we've got C3H8O3. There we go. That's the formula for glycerol. And those guys just remain intact. So the key point here is that the water molecules are not going to cause any disruption to covalent bonds, whether that be the covalent bonds within a polyatomic ion or whether that be the covalent bond within a molecule. the water molecules will cause ions to separate from one another. Okay, so this looks like we're doing a unit conversion here. It says calculate the mass of tetraborane that contains 1,000,000 boron atoms. So we've got two things to do. We need to go from boron atoms to moles of boron, and then once we have that, we can do the moles of B4H10, and then finally we can go on to grams of B4H10. So we really need to understand how to do all of these conversions. So to go from boron atoms to moles, we're going to use Avogadro's number. To go from moles of one thing to moles of another, we use what's called a mole ratio. And then to go from moles of something to grams of something, we use what we call the molar mass. So let's see how this all works. Now the key thing here is to commit to using dimensional analysis, or otherwise you're going to be in trouble. Our final answer needs to be given to 4 significant figures. So we got 1 by 10 to the 6 boron atoms, and then I've got to multiply it by a conversion factor to get to moles of boron. So I know that 1 mole of boron contains 6.022 by 10 to the 23 atoms. Should get into the habit of putting that last parentheses after I've written out my conversion factor. Okay, and so that gets me to there. Now I'm going to use my mole ratio. I get 1 mole of B4H10 for every 4 moles of boron. And I'm just getting those numbers from the formula. So that gets me to there. And then finally, I'm going to need my molar mass, right? So I want to go into grams of B4H10 that are in 1 mole. So, and again, I should put the whole thing just to make it really clear, B4H10, like that. So I'm going to need my molar mass. So I hop on over to my web browser, and I'm just going to go to my molecular weight calculator. There it is. And I'm going to put that in. B4H10. Always use a proper molecular weight calculator. Don't Google. Google will lead you astray, and you'll lose a considerable number of points if you use the wrong molar masses. 53.32. Now here's the hint. Before you put it into the calculator and get the wrong answer, cancel all your units, and most importantly, pay attention to what's left over. And in this case, what's left over is what I want, which is grams of B4H10, and that has to be to 4 significant figures. So there we go. So 1 by 10 to the 6 boron atoms times 1 mole of boron for every 6.022 by 10 to the 23 boron atoms. That gets me to moles of boron, times 1 mole of B4H10 for every 4 moles of boron atoms, times, and here we go, 53.32 grams of B4H10, for every 1 mole. And you don't have to put the divide 1 if you don't want to. You can, it doesn't make any difference, right? So there we go. And then to 4 significant figures, 2.214 by 10 to the minus 17 grams. And that makes complete sense to me, because 1 mole is around about 10 to the 24 atoms, and we only had 10 to the 6 atoms. So we should have a lot less than 1 mole. So that makes complete sense to me. It should have been a tiny number. All right, so a little bit confusing there. Not confusing, you just have to know what you're doing and not make shortcuts and not avoid using dimensional analysis, or otherwise you're going to get into trouble. Okay, calculate the volume in liters of a 0.032 mole per liter zinc nitrate solution that contains 6 moles of zinc nitrate. Give your answer to 3 significant figures. So we have 6 mole of zinc nitrate, and we are told that in 1 liter of this solution there is 0.0323 mole of zinc nitrate. And so that is it. It's literally just multiplying 2 numbers together. And I know I got it right because when I cancel my units, the only thing that's left over is liters. So when you interpret that molarity, what does it mean? It means you get 0.0323 moles of the compound for every 1 liter, or you can write in 1 liter there are 0.0323 moles. They are the same thing. And we're going to use it this way up so that we get liters. So whenever you're using a conversion factor, remember that what you're trying to remove has to be on the other side of the fraction. So on the the top versus the bottom when you're trying to cancel. So that's it. There we go. We know we got it right. We just got to round off to 3 sig figs now, and it's going to be okay. So 6 times 1 on 0.0323. Enter, and there it is. Yeah, that's a good thing. 3 sig figs is going to be 186 liters. There's no rounding errors or anything. I haven't done any intermediate calculations. There it is, 186 liters, which makes sense because you only get a fraction of a mole for every liter, and we want several moles. Perfect. Okay, here we go. All right, so a chemistry student weighs out 0.021 kilograms of an unknown solid compound X and adds it to 450 mils of distilled water at 19 degrees Celsius. And what happens? It all dissolves. So what that tells you is it is either perfectly saturated, like you got just the amount to get to the point where if you add any more, no more will dissolve, no more can dissolve, or alternatively it is what we call unsaturated. So then what they do is they add a little more, right? And in fact, what they add was 19 milligrams. Now, if after adding the 0.021 kilograms, it was saturated, what would happen is the 19 milligrams would just fall to the bottom. But in this case, that doesn't happen. The extra stuff dissolves. So what that means is you don't know you don't know how much it takes to saturate this solution because you haven't got to the point where no more can dissolve. What you would normally do if you're trying to figure out the solubility of something is you would make a saturated solution, you'd let all the solids settle out, and then you have the maximum amount dissolved. You would take a little bit of the liquid above the solid, and you would determine how much was dissolved in, say, 1 milliliter of that. So in this case, you can't use this information to calculate the solubility. So the answer is no. And the great thing about that is that you don't have to do the math to get the next bit. So the only way you can calculate the solubility is if you have generated a saturated solution, and you've got a saturated solution because when it either has some solid at the bottom, or when you add more, it falls out because you've reached the maximum amount that can dissolve. When you've got a saturated solution, what you can do is you can take a little bit of that out. Maybe you take 1 milliliter of it, or however many milliliters, and you figure out how much of the stuff is dissolved in there, and then you can say, okay, the maximum amount of grams that can dissolve in 1 mil is. But we can't do that in this case because we don't have a saturated solution. This looks very similar to the first problem. Names and chemical formulas of some chemical compounds are written in the first 2 columns of the table below. Each compound is soluble in water. Imagine that a few tenths of a mole of each compound is dissolved in a liter of water. write down in the third column of the table the chemical formula of the major chemical species that will be present. For example, you know water itself will be present, so you can begin each list with the chemical formula for water. So what we're going to do is make a comma-separated list. The first thing that we need to do is identify whether our compound is ionic or covalent. And in each case here, the formulas start with a metal. So we know ionic, ionic, ionic. So that means that each one of these is going to separate into cations and anions. We just have to figure out what is what. So every list is going to begin with water, because water is the major component that is present. We have many moles of water in a liter. So that's always going to be there. And then now we've got zinc ions and iodide ions. Now zinc is always 2+. It's one of our exceptions. So we know that this will be zinc 2+. And then iodine is in group 7A. So this means it will be I-. And the fact that these combine in a 1:2 ratio is consistent with the charges. Now for the copper, you get a little easier because it tells you that it's copper 2+, and then chloride is a monatomic anion. Chlorine is in group 7A, so it is also 1-, and then this 2:1 ratio between the chlorides and the coppers is consistent with the charges. We can see that by a crossover. Now for potassium cyanide, it's an ionic compound, so it's going to separate into ions, 1 cation, 1 anion. Potassium is in group 1A, so it always forms a +1. And as these guys combined in a 1:1 ratio, cyanide must be a -1. So there are our three lists there. Note that the covalent bond within the cyanide ion is not separated. So we're not going to write something like, I don't know, C2+, N3-, or some weird thing like that. That doesn't happen. The covalent bonds within a polyatomic ion are not able to be disrupted by the water. All right, we have the same thing again here. I won't read out all of the preliminary text here, but the important thing here is that we've got to identify whether the compound is molecular or ionic, or what we call covalent. So this is covalent, and it's not an acid because it doesn't have the word acid in the name. This is covalent. It's not an acid because it doesn't have the word acid in the name. And this is also covalent. All of them begin with a non-metal. None of the names here look like the names for ionic compounds. All right, so what does that mean? Well, water is always present as the largest component in this scenario. And then for molecular compounds, we just get the molecules are dissolved intact. They don't dissociate at all. So that makes it really easy. There's only two things present, water molecules and the molecules of the solute. Nice work, hey, moving pretty quick. All right, this one looks interesting. This is going to be about finding the mole ratio between phosphorus and sulfur in this compound. So it says X stands for a whole number. So the moles of P to the moles of sulfur is equal to 4 on X. And our job is to figure out what X is. Now, someone did some measurements and they say that a certain sample of an unknown compound contains 8.4 moles of sulfur. 8.4 mole of sulfur. I should put mole sulfur here. Oh, sorry, mole. This is mole P, and this is mole sulfur. This is 8.4 moles of sulfur and 3.37 mole of P. So I know that X is bigger than 4, don't I? Because from this sample. So all I've got to do now is solve for X, right? So X moles of sulfur. I'm just going to work on that. So this would be 4 moles of P times 8.4 moles of sulfur Just bringing that guy up there, and then I'm going to bring that guy over there, and then the 3.7 moles of 3.37 mole of P down there. And I know I got it right because moles of P, moles of P, moles of sulfur. So I just did some algebra there, and I want a number, I want X to be a whole number that is bigger than 4. Let's see what we get when we put those numbers in. Here we go. So we got 4 times 8.4 divide 3.37 equals 10. There we go. That's good. 10 is a number that is bigger than 4. And that makes sense because in our sample, the sulfur, we had a little over double the moles of the phosphorus. So X equals 10. So P4S 10. There we go. Now, this is a molecular compound, non-metals coming together, so we don't reduce it to the empirical formula. That's the convention. All right, P4S10, and yep, that's good. So in here, I kind of did the algebra. You might choose to do the algebra in more than one step. I would avoid doing that, but you might need to. I'm pretty good at rearranging these things. If you really wanted to, you can put that into an online solver and just have it solve for X for you. All right. The chemical formula for hydrogen bromide is HBr. A chemist determined by measurements that 0.09 moles of hydrogen bromide participate in a chemical reaction. Calculate the mass of hydrogen bromide that participates. Okay, so the conversion factor from moles to grams is simply the molar mass. So we can use dimensional analysis to help us here. 0.09 moles of HBr, and then I need to get rid of the moles, so I want moles on the bottom, and I want to turn it into grams, and the grams of HBr in 1 mole is simply its molar mass. So I flip on over to my molecular weight calculator, put in the formula HBr, hit calculate, watch it change, 80.91, and there we go. And then before I put it in the calculator, I'm just going to double check that I got the units left that I want, grams of HBr. We want this 3 significant figures, so that's it, right? 0.09 times 88.91, and so we got 8.00 grams. A nice round number. Okay, 3 significant figures, everything is good. Remember, trailing zeros count if the number has a decimal point. All right, that's good. We're good. Calculate the number of hydrogen atoms in a 50-gram sample of ammonia. So whenever you're going from amount of one thing, say let's call it A, and you want to end up with amount of something else, you always got to go through moles. You always got to go into moles. So if you never know what to do, make sure you go into moles first. So this is going to be my strategy. I'm going to go from grams of ammonia to moles of ammonia to moles of hydrogen, and then finally I'm going to go on to, and in this case we want the number of hydrogen atoms. And the conversion factors that I need to do this, to go from grams to moles, I've got to multiply it by 1 on the molar mass. To go from moles of one thing to moles of another, I'm going to multiply by what we call the mole ratio. We get 3 moles of hydrogen for every 1 mole of ammonia. And then finally, to go from the moles of hydrogen to the number of hydrogen atoms, I'm going to multiply it by Avogadro's number. And it's all about that dimensional analysis, right? As long as you keep the dimensional analysis straight, you'll be okay. So I've got 50 grams of ammonia multiplied by, and I know immediately that grams of ammonia has to go on the bottom and moles of ammonia should go on the top. And so this is the molar mass, and so that we're just going to, I know the molar mass, but I'm going to show good practice. 17.03 grams. And you can see that that will get me to there. Now I use my mole ratio from the formula. 3 moles of hydrogen for every 1 mole of ammonia. We always just get mole ratios either from the formula or chemical equation. And then finally, Avogadro's number. And what do we know? 6.022 by 10 to the 23 hydrogen atoms are in 1 mole of hydrogen. And there we go. Before I put anything in my calculator, I'm going to cancel all my units. And I'm going to double check that the only unit that remains is what I want, which is what I got. And then I'm going to think about my Sig Figs, and my Sig Figs in this case were 3 significant figures. So I'm going to make sure to round to 3 significant figures. So what do we got? 50 grams of ammonia. We get in every 1 mole there are 17.03 grams. We get 3 moles of hydrogen atoms for every 1 mole of ammonia, and there are 6.022 by 10 to the 23 hydrogen atoms in 1 mole. So it should be a big number. We had multiple moles of ammonia. Think about it, 1 mole is 17 grams, so we had about 3 moles of ammonia. So we should have had about 9 moles of hydrogen atoms, which we do. So 5.30 times 10 to the 24 hydrogen atoms, right? So that's what we've got there. All right, so that'll be cool. That's it. It all makes logical sense. We have knowing that 1 mole is 6.022 by 10 to the 23 hydrogen atoms. We have multiple atoms. We have about 9 moles of hydrogen atoms, so that number makes sense. All right. Okay. So this looks like it's all about moles per liter, or in particular in this case, micromoles per liter. So we have to keep an eye out for these prefixes. So it says, and if you go into the data section, it has a list of prefixes in there. It's the very first item in the data section. So you should never make an error using prefixes. So it says a chemist adds 1.4 liters of 0.064 micromole per liter potassium permanganate to a reaction flask. Calculate the millimoles of potassium permanganate the chemist has added. So this is what I'm going to do. I'm going to go from liters to micromoles to moles. Yeah, and then finally I'm going to go on to millimoles. Alright, so that's how I'm going to do it. So I'm going to go 1.40 liters, and I get, we want liters on the bottom here, in every 1 liter, 0.064 micromole. There it is. And that gets me to there. Now I know that 1 micromole is the same as 10 to the minus 6 moles, so that gets me to there. And then finally I know, I'll put mole on the bottom there and millimole on the top, that in 1 millimole there are 10 to the minus 3 moles. So liters goes, micromoles goes, moles go, and the only thing that I'm left with is millimoles, which is exactly what I wanted. So let's see what that looks like. 1.4 times 0.064 times 1 times 10 to the minus 6 times 1 divide 1 by 10 to the minus 3. So there we go. 8.96 by 10 to the minus 5, and we were asked to give to two significant figures, so this is just going to become 9.0 by 10 to the minus 5 millimole. There we go. Alright, not too bad, getting there. So being really good with creating these conversion factors. Remember, when you create a conversion factor for converting between systems within the metric system, the 1 always goes beside the unit that has the prefix, and the power of 10 always goes beside the unit that doesn't have the prefix. People get into weird situations when they start doing things like this. 100 centimeters is 1 meter. That's not how the metric system is intended to be used. You might find that easier for the simple cases, but it comes back to bite you in the butt later on. You want to get used to using this system. Instead of writing that, we should do the following. 1 centimeter is the same as 10 to the minus 2 meters. Okay, so yeah, you know, the sort of, how would you say, simplistic way of doing it will lead you astray later on, and you'll have a lot of troubles in general chemistry. So we want to get this right now. The other thing that you should be taking care to do is to familiarize yourself with entering in scientific notation properly into your calculator. The sooner you do that, the better off you will be. A lot of people are resistant to it. I'd encourage you not to be. Okay, a chemist weighed out 7.25 grams of nickel. Calculate the number of moles of nickel that she weighed out. That's not too bad. 7.25 grams of nickel. Multiply it by, we need the conversion factor that has grams of nickel on the bottom and moles of nickel on the top. And that's what we call the molar mass. So in 1 mole of nickel, and we can either look this up in the periodic table or we can use our molar mass calculator. 58.69 grams, and that's it. Before we enter anything into the calculator, we always check that we have our units that we want. That's what we want, and we want 3 significant figures. So that's it. 7.25 times 1 on 58.69. It should be less than a mole, right? Because we don't have a mole. So there we go. 0.124 moles. All right. A little over 1/10 of a mole makes perfect sense. Okay. We're getting close, aren't we? Ammonium perchlorate is a powerful solid rocket booster used in the space shuttle boosters. It decomposes into nitrogen gas and chlorine gas and oxygen gas and water vapor. So what they're really saying when they say decomposes is you just have this thing and it just falls apart. So they're really giving you a chemical reaction here that we can go ahead and balance, right? That's what they're really giving you. Giving you a chemical equation that they want you to go ahead and balance. So we can see we need 2 nitrogens on the left. Then you can see we need 8 hydrogens on the right. So we need 4 of those guys. And then you can see that we're going to need, we've got 2 chlorines on the left and we've got 2 chlorines on the right. So chlorines look good. And then finally we've got to get oxygens to work out. So we have 8 chlorine oxygens on the left. And we've got 4. So you'll put a 2 there and then everything should look good. So let's see what we've got. Nitrogens, 2 on the left, 2 on the right. They are good. Hydrogens, looks like we've got 8 on the left, 4 times 2, 8 on the right. So they are good. Chlorines, we have 2 on the left and 2 on the right. And then finally oxygens, 2 times 4, that's 8. And then 2 times 4, that's 4, plus another 4, that is 8. So that is a balanced chemical equation for this decomposition, right? Okay, so now what do we got? It says calculate the moles of ammonium perchlorate needed to produce 2.2 moles of oxygen. 2.2 mole. So when we go from moles of one thing to moles of another thing, we know that our conversion factor is what we call the mole ratio. Okay, and we can see here that our mole ratio is really quite simple, because for every 2 moles of O2 that are produced, we require that 2 moles of ammonium perchlorate are consumed. So they're actually going to be the same number, aren't they? But let's just see how it works. 2.2 mole of O2 times, and from our balanced chemical equation, we see that we get 2 moles of ammonium perchlorate consumed for every 2 moles of O2 produced. And so moles of O2 cancels, and we end up with 2.2 mole of ammonium chloride. And you can see how the units really keep us on track, right? This is really kind of quite important that we do that, or otherwise we end up making dumb errors that we can't detect easily. All right, we're getting near the end here, so that's not bad, right? So it says a chemist weighed out 4.9 grams of iron. Calculate the number of moles of iron she weighed out. So again, 4.9 grams of iron multiplied by, we need grams of iron on the bottom line, and we need moles of iron on the top line. That's just what we call the molar mass. So we go to our periodic table or to an online molar mass calculator, and we go Fe for iron at 55.85 grams in 1 mole. 55.85 grams in a mole. Check our units before we put anything into the calculator, and we know that we've got it right, and we want 2 significant figures. So really, you know, everything should be a foregone conclusion before you put it into the calculator. Now, 4.9 grams is going to be a little less than 1/10 of a mole, so we want a number that is a bit smaller than 0.1. See what we get. There we go. So to 2 significant figures, this is going to be 0.088 moles of iron, which is a little less than 0.1. Looking good. All right, 14. What do we got here? Oh, this looks really similar to what we had before, but it's about the molarity concept, right? The moles per liter. So it says a chemist prepares a solution of potassium permanganate by measuring out 27 micromoles of potassium permanganate into a 500 ml volumetric flask, and then filling the flask to the mark with water. So calculate the concentration in moles per liter. So I have to figure out the moles of my potassium permanganate, and then I have to figure out the liters of solution. Now I'm given some information here. I've got the volume of the solution, but it's expressed in milliliters, so I'm going to have to go milliliters to liters. And then I do have the amount of potassium permanganate, but it's expressed in micromoles. Now I'm going to make this real simple, right? That's what we want to do, moles of potassium manganate over liters of solution. I'm going to show you how to use prefixes to make this happen. So we had 27 micromoles. Another way of writing micro is just to write by 10 to the minus 6. So that would just become that. And then we had 500 milliliters. So because remember that micro just means times 10 to the minus 6. We had 500 milliliters, remembering that milli just means times 10 to the minus 3. Instead of writing milli, I'm going to write times 10 to the minus 3 liters. And there I am, done in one step. And what are my units going to be? Moles per liter. Now, just got to put that into my calculator correctly. 27 times 10 to the minus 6 divide 500 by 10 to the minus 3. Booyah. And there we go. We want 2 significant figures, so this is perfect. 5.4 by 10 to the minus 5 moles per liter. Easy, all right? Easy, easy, easy. Okay, here's another one. Calculate the number of oxygen atoms in a 120 gram sample of Phosterite. So we're going from amount of one thing to amount of another. So remember what I said, we always want to go through moles before we do this. So I'm going to go like this. I'm going to go from grams of Phosterite to moles of Phosterite, and then from there I'm going to go to moles of oxygen, and then finally I can get that into whatever units I want, which was number of oxygen atoms. Okay, so how do I do it? To go from the conversion factor between grams and moles is the molar mass. So I'm going to times by 1 on the molar mass in particular. To get from moles of one thing to moles of another, I'm going to multiply by a mole ratio, which in this case we get 4 moles of oxygen for every 1 mole of the Phosterite. And then to go from moles of something to the number of atoms, I'm going to multiply by Avogadro's. So just knowing those conversion factors, and there's lots of diagrams that you've been presented with that will help you do that, that's going to be, that's really what you want. You want one of those diagrams that shows you how to move around these conversions on hand, and you want to know how to use it. So we've got 120 grams of Mg2SiO4, and so my first conversion factor has to have grams of Mg2SiO4 on the bottom, and I want to be turning that into moles of Mg2SiO4. This is what we call the molar mass, the number of grams in 1 mole. So I'm going to go over to my molar mass calculator, Mg2SiO4. It's going to be a little bigger than some of the previous ones, 140.69. Okay, so that gets me there. Now, what's my mole ratio? I mentioned it before. You get 4 moles of oxygen for every 1 mole of your compound. So that gets me there. And then finally, Avogadro's number, 6.022 by 10 to the 23 oxygen atoms for every 1 mole of oxygen. So let's see what we've got here. Grams of Phosterite cancels, moles of Phosterite cancels, moles of oxygen cancel. There's only one thing left over, and that is oxygen atoms, which is what we want. So we've got 120 grams of the Phosterite, which is a little less than 1 mole. So we would expect to get a little more than 4 moles of oxygen atoms. So it's going to be a number that's bigger, about 4 times bigger than Avogadro's number when I do this. So we got 120 grams of Phosterite times 1 mole of Phosterite per 140.69 grams times 4 moles of oxygen atoms for every 1 mole of the Phosterite times 6.022 by 10 to the 23 atoms of oxygen for every 1 mole of oxygen, and I ended up with 2.05 by 10 to the 24 oxygen atoms, which is more than what's in a mole by about a factor of 4, which is what I was expecting. All right, cool. Last one, here we go. This one looks like it's about solubility. Now, there's a nice little table that explains about solubility. So gases, and then we have solids and liquids. And there are 2 things that affect the solubility, right? There's the pressure and there's the temperature, right? And for gases, as the pressure goes up, the solubility goes up. For gases, as the temperature goes up, the solubility goes down. For solids and liquids, as the pressure goes up or down, there's no effect on the solubility. But as the temperature goes up, the solubility goes up. So that information is in the explanation for these types of problems within ALEX. So that's what we want to keep in mind. So when you're looking at all of this stuff, that's what's going on here, right? So what is dissolving? Is it a gas? Is it a solid or a liquid? Two 250 ml samples of water are drawn from a deep well bored into a large underground salt deposit. Now, NaCl is a solid at room temperature. It is an ionic compound. Sample 1 is from the top of the well and is initially at 42 degrees Celsius. So let's just make a note of that. T1 equals 42 degrees Celsius. And then sample 2 is at a depth of 150 meters and it's at a temperature of 8 degrees Celsius. Okay, so what we're saying here is sample 2 is at a lower temperature, and we know that for solids, as the temperature goes down, the solubility goes down. Both samples are allowed to come to room temperature. Okay, so sample 1 is going to cool down, and sample 2 is going to warm up. So as sample 1 cools down, what's going to happen is that the salt will become less soluble. So in this case, you might see what we call a precipitate forming, right? That solid is going to fall out. In this case, maybe if we have enough, if it is actually saturated, right? In this case, we're warming up, so it actually would kind of make it easier for things to dissolve in it. The pressure doesn't change in each case. So what will happen, it says a bigger mass of NaCl will form in sample number 2. Well, that's ridiculous because we won't get any precipitate occurring, right? We see here only sample 1 forms a precipitate. A smaller mass of precipitate will form, no, because it will actually become warmer, so more could dissolve. That's ridiculous. The same mass, no, because it's becoming warmer, we won't get any precipitate in sample 2. And then the answer is this one, no precipitate in sample 2, right? Because we're warming it up. So you only get a precipitate when you cool it down and the stuff becomes less soluble. All right, guys, so that's a practice test 3. I hope that it was helpful. And yeah, good luck. All right.